So yes, this is where we stopped, and I left when I had said that we shall look at the divergence of B. Now the Biot-Savart law, for the general case, of volume current distribution, of density J. So if you have a volume created by the current density J, then you would have that the B, the magnetic flux density in this region, would be the same as mu naught over 4 pi integral over the volume tau J cross R over R cubed. And this is integrated over the volume created by this current tau. Now this formula, gives the magnetic flux density, at a point in space T, X, Y, Z, and in terms of the conductivity, in terms of the current density, in terms of the current density J, at another point in space which we can call P, X prime, Y prime, Z prime, and we can express this diagrammatically with the diagram of our volume of current density J. So here we have a volume. You can draw it the way you wish, and maybe try to be artistic, trying to make sure it looks like a volume, as in I could have shaded it, but I'll try to, maybe I can shade it. Why not remind myself of the art. I want to make sure that it looks like a sweet potato. Like a sweet potato. Huh? You see, I told you that my nephew said sometimes that I speak dirty English. But when he came here this time, it pleased me. In the holiday, he didn't remember that I used to speak that English. He was comfortable with my English now, after growing up. So maybe when you grow up also, you'll be comfortable. So we have our elemental volume, which is a cube, and from this cube we can take a point, the distance R, and this is our point P prime, x prime, y prime. I think these are not prime, if I can recall. So we have a formula giving the magnetic flux density at the point P in terms of the current density J. So we are looking at this point P, x, y, z in terms of the point P prime with x prime, y prime, z prime, which is being threaded by the current. So the current which is threading this volume is the one which is producing a magnetic field at a point in space P, x, y, z. And this is an elemental volume, the tau. So we can explicitly state that. We can explicitly state that the B, or the magnetic flux density, will be a function of x, y, z, and then the current density also would be a function, of x prime, y prime, z prime, because the current density is threading the volume. So it is a function of the primed coordinates. But the magnetic field which is being felt at the point P is a function of the unprimed coordinates x, y, z. So if we took R to be the position vector, this would be the same as, who can guess? Out with these 2 points, P and P prime and P, when you want to get the position vector between them, how do you get the position vector? R of equal to? Can I put a cursor up? Smallest one is how much? What? The smallest in the paper is this one. So tell me.
So is the square root of x minus x prime.
X minus
X prime.
this is like this. It is equal to
X minus x prime then squared.
x minus
X prime. Okay, bracket bladder square. That is x prime is very.
this one here.
Yes.
Okay.
Plus you did the procedure for y.
Now, I've already got you. If that means now all of you. The cassava is always a hit and run. And the first person either takes the cassava or, because when the first person fails, then it means that you now have a clue of what is going on. How can I get a vector even in a scar? So the integration is over the prime coordinates, because we are integrating due to the number of the current density around here. So it's over the primed shall do the integration over the primed coordinates. So the divergence, yeah? They have told you. Prime. Yeah, prime. So the divergence and the curl, the divergence and the curl are to be taken with respect. Now when you are now trying to make them diverge, when the field lines are diverging, they are going beyond the prime. So you have to take, and also when you are curling them, trying to curl them, you're also going beyond the volume, because these field lines are going beyond this volume up to the point of interest where you are looking for this magnetic flux density. So that means we shall be taking it with now the unprimed coordinates. So will be taken with the respect to unprimed coordinates. You are lucky. There are people who think I can't make a joke. They think I'm the meanest guy on planet Earth because they see me pass to and fro. Not even a smile. I walk as if. Thus, taking the divergence of the equation, for B yields that the divergence of B is equal to mu naught over 4 pi integral. Then we take the divergence of this whole thing, which would be the divergence, and this is still over the volume tau, divergence of J cross R over R cubed d tau. So using the vector identity, that the divergence of the cross product of two vectors F and G is equal to one of the vectors dotted with the curl of the other minus F divergence the curl of the other vector. Where so if I can now wrap this nice thing. So if B is equal to J and F is equal to R over R cubed, then this would imply that the divergence of J cross R over R cubed would be equal to G. I think that is, I still, always I was supposed to be making this correction a long time ago, but I don't know why. So if that is the case, that means we would have the, it's a reverse. Because what I got here is R over R cubed dot J minus J dot the curl of R over R cubed. I think according to the identity, then we should change this reverse, isn't it? It's something I was supposed to be corrected. So this should be F, and this should be G. I guess now there is a net. So I'll be having the divergence of, so the inside has been made very nice, that instead this now was improved into this over R cubed. Because it doesn't change anything. R cubed is a scalar, so it doesn't affect the cross product. Okay, so this would be the same as minus J dot the curl of R over R cubed. Since the curl of J is equal to 0, since the curl of J is equal to 0, because why would we have the curl of J being equal to 0? Huh? I mean, we are saying that this whole thing will be equal to 0. That's why we are getting our divergence of J plus R over R cubed is equal to minus this, since this is equal to 0. What would make, yes, Emma?
Since J is proportional to electric density, we know that the curl of E equals to 0, which implies the curl of J should also be equal to 0.
Okay, fair, but yes.
J is a function of x, y, z. It's not a function of x, y, z. So that means it will be a constant for the rest of that curve.
I think you deserve the cassava. Oh, this was one of us.
Second try.
No, I had not put a cassava. But just because the way he did it, he deserved the cassava. I'm a generous guy. So the idea is that the integration is being done over the prime. Integration is over the prime, and then we are having our when we are taking the curl of J. Or in other words, you can say that because J does not depend on unprimed variables or coordinates. Variables, or you can call them coordinates, which are x, y, z. He's a rich man by heart. Not by the cassava I gave, but now he's, and you are going to get money. I bless you in the name of physics. You get money and failing to get where to keep it.
What about
R over R cubed is the same as grad 1 over R. So this hence we would have that the divergence of J cross R over R cubed is equal to minus J into the curve of the gradient 1 over R. So I use these brackets. This one is okay. And this we say equal to 0 since grad 1 over R equals to, so grad means the grad operator is equivalent to when I do that. So grad 1 over R means that it's equivalent to grad of 1 over R. So this now gives us an idea that the divergence of B, which was on the left side from where we began from, I've just rubbed it off. I don't need to rub it off. We started at this part, that the divergence of B on the left is equal to mu naught over 4 pi integral over tau. This. We have worked out this part and everything went to 0. So that's why we are saying that thus finally the divergence of B is equal to 0. And in integral form, we have that the integral over the closed curve C d dot L is equal to mu naught I enclosed. Not sure whether we are together. So I know you're having a lot of questions here. Anyone who can volunteer? No cassava. There is a cassava. So who can volunteer how this is being the same as the gradient of 1 over R?
By writing or
By what?
is it by writing or by talking? Demonstrating the show or
No. Just to explain how the ratio of the position vector and the position vector cubed is similar to the gradient or grad 1 over R.
Okay, now the position vector over R should be the same as 1 over R squared in the R direction. Then from there, if you interpret that thing, if you go back like you get a grad, since it is in the R direction, it's just like differentiating 1 over R with respect to R.
Anyone clicking?
The first statement is like negative 1 over R squared in the R direction. That is
In the other direction like this?
yes. So now, if you compare with the first one,
This one here.
yes, you go back to that one.
I'll be able to come back here.
Yes. So now even if you differentiate now 1 over R,
This one here.
yes, you still go back to the other.
So we are okay.
Yes.
Fine. That's what I wanted to enjoy. So no, we've almost taken the whole hour just making fun, and we only written a little bit of this. So this now takes us to the magnetic vector potential. Magnetic vector potential. Magnetic vector potential. And we know from here, when I hear something I've written there, we already now know that the divergence of B equals 0. So we know that the divergence of B is equal to 0. What was the divergence of E from electrostatics? Epsilon. So the vector identity divergence of the curl of A is equal to 0. Hence, B can be expressed as B equals to the curl of A. I find this statement very confusing, as if you are just trying to forge up things to get what you want. I don't know whether you agree with me. We've said the the divergence of B equal to 0. And then we say, if we took an identity of this nature, and then we say that B is equal, doesn't make sense in a way. But for the benefit of what we are doing, we shall say where A is the and this is how the stuff is in the books as well. So that's why I'm trying to tell you that sometimes we do things just because, and that's the beauty of physicists and mathematicians. We are the bosses. We don't care. We just say pressure X is equal to force P over area Q. And you say where X is the pressure, P is the force, and Q is the area. And people shout, but area is A, and force is F. I don't give a damn on that. All I know is that I know I have defined my variables which I've used. I've defined them. The symbols are defined. So, but if you wrote this for an S2 kid, the kid will argue with you. No. Our teacher says P equals to F over. But if you state this for me and you don't define your P, F, A, I don't know them.
I say symbol
And what is the usual meaning? And there are very few symbols which have their usual meaning. For example, epsilon not really may mean its usual meaning, because in the books you find epsilon not equal to 8.85 times 10 to the power negative 12 Faraday per minute. Mu naught may have its usual meaning, equaling to 4 pi times 10 to the power negative 7 per minute. So where A is the magnetic vector, so which is where A is expressed or can be expressed as B can be expressed as that, where A is the magnetic vector potential. magnetic vector potential. So according to Biot-Savart, law, before I forget, are we in for tomorrow?
Yes.
7 a.m. I want to make sure that we agree, since you said you forgot. I want to make sure we agree now so that if you are not there, then I take a note. So it's a deal? Thanks. So according to Biot-Savart, where we have our circuit, remember, we have our circuit, and our circuit is having our supply of current from a battery, plus, minus, with our current moving in this direction. And if we took an element on this circuit, around this place here, you can shade it like that. And from this element, which is at P, X prime, P prime, X prime, Y prime, Z prime, with our DL as the elemental length, if we took another point P, position vector R, and it is at a point P with unprimed X, Y, Z, we have our magnetic field, which I can make point in that direction B. So we can follow it up. But the magnetic flux density felt or experienced at the point P the magnetic flux density felt at the point P would be the same as mu naught over 4 pi integral J cross R over R cubed, and we integrate over the volume, tau. But we know that the grad of 1 over R is equal to minus R over R cubed, which is equal to R roof over R squared. And this would imply that B at P would equal to mu naught over 4 pi integral grad 1 over R, the curl, cross, not the curl, cross J, the tau, and we can call this one our equation 1. Using another vector identity, we would have that the curl of a scalar multiplied by a vector is the same as grad scalar crossed with the vector plus the scalar into the curl of the vector, and this is our equation 2 to express the vector identity, where the F in this case is a scalar, and in some books you'll find that the F can be expressed as phi to represent the scalar. In other books they make it phi, is it phi or what is the difference between this and this? One upside is this one. Actually, which sometimes in quantum mechanics is a bit nicely made as if it is a glass of wine with badly shaped. So where F is a scalar and this scalar, then we will get that the grad 1 over R cross J would be the same as the curl of J over R minus 1 over R into the curl of J. And this is our equation 3. This is basically by having we are taking, if we took this to be, so the curl of J over R, I'm just trying to relate the, so we have 1 over R as the scalar and J as our A. So our 1 over R is the scalar, the F, and the A is J. So that we have that the grad 1 over R cross J is equal to the curl of 1 over R times J. This is J over R minus 1 over R, then into the curl of J. That's how the identity has been invoked. But the current density J is a function of what? In terms of the primed and unprimed, is a function of the primed ones, because the primed ones are the one, or are the part of the circuit, or the volume which is threaded by the current. So we get and the operator and the grad operation operates on the unprimed coordinates or variables, implying that 1 over R, the curl of J comes to 0 again. So equation 3 becomes the grad 1 over R cross J would be equal to the curl of J over R. This gives our equation 4, and equation 1 now reads, that B at P is equal to mu naught over 4 pi integral. I now have the last bit being this one here, which would be the curl of J over R. This mosquito is not shy. He wants to eat me when I'm saying. Should wait for when people go to sleep. So now that I already have the equation 1, I can say that this equation 1, or we can write it as, it can be written as B is equal to mu naught over 4 pi, and then integral naught. because I want to make sure that this curl can be put outside, so that I take the curl of the integral, so about that, so that I get the curl of mu naught over 4 pi, then integral, I get the j over r as the integrand, then the tau. This becomes our equation 5. Equation 5 is in the form, equation 5 is in the form, equation 5 is in the form B is equal to the curl of A. And there is 6. Comparing 5 and 6, after writing it in a nice way, comparing equations 5 and 6, we will get that our A, if this B is equal to the curl of A, so A is the whole of this curl here, so which would be the same as mu naught over 4 pi integral j over r d tau. That gives us what we call our magnetic vector potential, and we can baptize this our equation 7, where as we have come this far, A is the magnetic vector potential. Now, since j that tau, since j that tau is the same as j dl, so for line currents, you know, we have surface current, volume current, and line currents. A would be equal to mu naught I over 4 pi, and then we say that, sorry, this is supposed to be, this should have been I. This is I dl, not j dl. Then this should be the same as mu naught I integral dl over r. It's the current density, so we normally say this is the current over the area, but if you have line currents, then it will be current over. When we talk of surface charge density, we talk of charge over area. Volume charge density, charge over volume. So when we talk of this being a line of the line currents, their density would be and for, so this becomes our equation 8. And for surface currents, then we would have that our A is equal to mu naught. Of course, our J dot tau will be the same as J dot ds. So this will be mu naught over 4 pi integral Js surface current density dot ds divided by r. And this is our equation 9. Of course, where now Js, where Js is the surface current density. Now, if the current is itself, if the current itself extends to infinity, if the current itself extends to infinity, equations 7, 8, and 9 no longer hold. Why? Why wouldn't they hold? They will no longer hold because if we took the case of our biosivar case, which we last drew, where we have our circuit and we have our element here, this element here, and we are having our point where we are getting our D, and we are having our R. So this is the R. So which R is in our 7, in our 8, and in our 9. So if the currents extend and keep going, that means you're extending to infinity, means that you are having this distance becoming large and large, and the more you divide by, if I came with 42 sweets, each one of you would get a sweet. If now I double your number, I keep doubling your number, tripling it, 100 in it. Is it 100 in it? How is it? Making it 100, multiplying it by 100-fold. Then I will end up having nothing to give, even if I smash it. Even if I smash these pieces of sweets, I wouldn't be having anything to give anybody. But for a special case, there are special situations. Where the magnetic vector potential A may be obtained. Even with the constraint of making the currents go to infinity, and this may be obtained from the integral A dot dl being the same as the surface integral, the curve of A dot ds. And this is since, I can put it on the other side. So since our curl of A, when you curl the magnetic vector potential, you get the magnetic field density. Of course, if you curl the magnetic vector potential, it means you are now going to get the density, meaning that you are similarly looking at the number of the strength of a given magnetic field. So since we have that equal that, we get that the integral of A dot dl is equal to the surface, and because this is equivalent to B, so we get that this is B dot ds. And that's what I was trying to tell you, that when you get the magnetic field lines and you try to take their curl, not field lines, if you get the magnetic vector potential and you try to take its curl, then you are looking at the number of magnetic field lines in a given area. If you took those which are perpendicular to the area, then you get what we call in the magnetism the flux. So the magnetic flux, you get this, which is the magnetic flux that would be threading that whole surface. Threading the surface. So now we know how the expression for the magnetic vector potential comes in. The expression for the flux, which is the same as, we said that if you have a coil, okay, and it is in a magnetic field, don't draw this, doing this for the sake of understanding. When you were to look for the flux, you had to first make sure that if this is the direction of B, you first take the plane of your coil. So the coil is, oriented at this point. So you have to first take this is its plane, and then you take the normal to the plane of your coil, which will be this. And it is along this normal that you would now have that if this is your B, and this is your normal, so if this is theta, the angle between the magnetic field and the normal to the plane of the coil, this is the plane, assuming this is my coil, you guys can make it circular, then we have to say that flux phi is equal to the B component of B along this place, which is B cos theta. So this is B, like that. So this is B cos theta. And then you multiply by the area which I am using this area, the area of the coil through which all these magnetic field lines are threaded. And of course, when you look at this would be the same as B dot NDS. And when you take the cross product, it would be B times, this is already a scalar, but the magnitude of these two gives you ds, and then you take the cosine of the angle between these two, whereby, of course, when you take this would have been our yes. The small, if you just took a small piece of the plane on this, or a small piece of the surface enclosed in the plane of the coil. And so that's how everything comes up. Of course, when you take this is d ds, so you get d ds cosine theta from the magnetism part, which you have all forgotten. Okay, so let's work out an example. Let's work out an example, and this example is to find the vector potential, find the vector potential of an infinite solenoid, with n turns per unit length. Per unit length, radius r, and current I. And current I. So what are we talking about? A solenoid is a coil wound on a cylindrical form whose length is about 10 times its diameter. So if you have anything, so if I get my two lines and I try to wind out, if I try to wind out my, wires, my wire around this, and I take this one into the other side, if the diameter here, and compared to the length L is about greater or equal to 10B, then this qualifies to be called solenoid. So I can draw our example solenoid, whereby we have can take this to be like that. So I can draw it the other way to just have variety. Of course, there are a bunch of, a lot of windings, but I'll choose to do those couple. This one goes down, so this one goes the other side, comes up, and goes the other side. So the flux is equal to B A, which is area times the y is it equal to B A? If I curl my fingers in the direction of the current, the field will be along the thumb. That means if I took the cross-sectional area where the field is threaded, it means that the field is perpendicular to the cross-sectional area. So we don't need to decode angle between them. That is, the field lines and the normal to the area are parallel to each other. So the cosine of 0 is 1. Since the current, and of course I have drawn these pieces like this because we said it is infinite, so it extends this side and extends the other side. Such that since the current extends to infinity, since the current extends to infinity, we cannot use equation 8. We cannot use equation 8, if you remember it well. The 8 one was for surface current density, which was mu naught alpha pi integral j dot ds over r. And if that is the case, but the direction of A, the direction of A, so she's being called to ask him what is happening, you are not coming. Mimics that of the current. Mimics that of the current. So we consider the Amperian loop. Consider the Amperian loop. Let's Amperian capital A. The Amperian loop at radius R inside the solenoid. So when we do that, we get the integral A dot dl being the same as surface integral B dot ds, which is equal to mu naught ni into pi r squared. The left-hand side implies that the integral B dot dl is equal to A into 2 pi r, and thus we would have that our A is equal to mu naught Ni over 2 r of phi roof. And this is for not for A, but for R, or for when you go outside the solenoid. I used to give this as assignment. Why have I done it today?
Excuse me.
Yes.
It's supposed to be A dot dl. This is A dot dl. That's to be yes. It's A dot dl. But that's how the basic come. First the dl is what is come back to pi.
Oh yeah, here. This is A dot dl. Okay. I still have many minutes, so I know I will be able to cover what I wanted to cover today. So for an Amperian loop, for an Amperian Amperian loop. Then we got, which is when we take an Amperian loop outside the solenoid, the flux is B dot S is equal to mu naught NI into pi r squared. Is there no problem? So since the field only extends out to R, then we will have that our A into 2 pi R is equal to mu naught Ni pi r squared. Therefore, this should be M, not here. I'll put the vector somewhere. This would be mu naught Ni r squared over 2r. This will be along the phi. Because a solenoid is cylindrical, okay? And we are considering this vector potential along the, remember when we tried to curl, A is when we looked at the flux. So we are trying to look at along the cross-sectional area, and that cross-sectional area part is where we are looking at the phi as the angle made. I'm sorry if these things are looking to be too many, it's because mine, I don't realize it. They are somewhere hidden, somewhere inside my things.